Hi, I'm Rebecca, and I'm a graduate teaching assistant here in the Department of Kinesiology and Health Promotion at the University of Kentucky. Today in this video, you will learn how to perform a hydrostatic weighing test, as well as reviewing how the test and its measurements are interpreted to reflect body composition analysis. Hydrostatic weighing is a densitometry measurement technique used to determine body composition from body volume. Learning how to perform body composition assessments such as hydrostatic weighing or more commonly known as underwater weighing will allow you to better understand an individual's health status or optimize their performance goals. In addition, understanding how to interpret these calculations and results will give you a broader understanding of various components and compartments of the body, and theoretical and known assumptions which affects the validity or the accuracy of body composition analysis. Therefore, the purpose of this lab is to become familiar with the procedures of underwater weighing as well as the measurements it provides. Many techniques are used to measure or estimate body composition, such as the bod pod, DEXA, BIA, and skin folds. You may or may not be familiar with some of these techniques, but what I want you to understand today is that each of these body composition techniques or methods is primarily based on one of the primary components of the body, and relies on an assumption that underlines the accuracy for estimating the component of total body composition. For example, the DEXA measures or estimates bone mineral content, bone mineral density. BIA measures or estimates total body water, or underwater weigh-in and bod pod, which measure or estimate total body volume, which body density can be derived from. Underwater weigh-in applies a two-component model, fat and fat-free mass, to estimate or evaluate body composition. The majority of fat mass is adipose tissue, while lean mass or fat-free mass is representative of protein, muscle, bone, which is mineral, and total body water. Fat density is 0.19 kilograms per liter, and fat-free density is 1.1 kilograms per liter. These measurements were obtained from the dissection of a small number of young white male cadavers. The underwater weigh-in technique also relies on the Archimedes principle, which states that the volume of the weight is equivalent to the volume of the liquid displaced when an object is submerged into water. Therefore, when we completely submerge an individual into the water, the weight lost by that individual is equal to the volume of water displaced, or the body volume of that individual. Underwater weigh-in test provides an indirect measure of body density. The underwater weigh-in test itself provides a measure of body volume, which we can then use to calculate an individual's body density by dividing the dry land weight of that individual by the body volume. When performing an underwater weigh-in test, it is important to remember that there are underlying assumptions for determining body composition measurements from the body density measurement. One is the separate densities of each body component are known and additive. Two, the density of the elements of the body are relatively constant from person to person. 3. The proportions of the elements other than fat are relatively constant from person to person. And the fourth and final assumption is that the person being measured differs from the standard reference body only in the amount of the body fat. We can then estimate an individual's percentage body fat by using the body density equation, the Surrey equation, which was derived and published in 1956. In addition, we can estimate the proportions or the percentages of each component of the body relative to the amount of fat or fat-free components, or relative to the body weight based on the theoretical densities of each component. For example, if our individual has a dry land body weight of 100 kilograms and a body density of 1.0400 kilograms per liter, we can then use the Surrey equation to calculate the percentage of body fat of 30%, which means that 30% of the individual's body mass weight is fat, or 30 kilograms of this 100 kilogram person is fat. Knowing the percent fat, we can then use a simple subtraction to determine the fat-free mass. Therefore, the 100 kilogram body weight minus the 30 kilograms of fat equals 70 kilograms of fat-free mass. For this lab, we will be measuring an individual's body volume to estimate their body composition by using underwater weighing test. Before we ask our participant to get into the tank, we need to take a few measurements first. The participant's age, height, and dry land weight need to be recorded. The participant should be measured in what they will get into the tank with. The participant's residual lung volume, RV, is measured or estimated by a recorder. RV is the small amount of air left in the lungs after a maximal exhalation. RV must be measured to account for its effects on the buoyancy when our participant is underwater. Here we are calibrating the RV recorder. We are filling the black bag up with 100% oxygen and measuring it to 5 liters. Being careful to take any excess oxygen out so we know exactly how much air the participant is breathing in, because at the end of the RV measurement, they will take a deep inhale and breathe in that 100% oxygen, and this allows us to see the impurities once they breathe all of their air out and take a deep breath of pure oxygen in. It is important to fully explain what the subject will be doing. They will first breathe normally until instructed to take a deep breath out, exhaling all of the air they can out. Then they will take a deep breath in immediately, breathing in that pure oxygen, and then continue to breathe normally until we say to stop. They are also wearing a nose clip at this point to ensure that all the air goes in and out of their mouth and none of the airs escape through their nose. The RV measure gives us the beginning alveolar air. After the exhale, which is the big dip that you see on the screen, we get what's called an impurities value. This is the amount of gas mixture that's left in the lungs that we cannot breathe out. If we breathed everything out, we would not have any air left in our lungs and our lungs would collapse. This impurity value is important for that reason. Next, we get an equilibrium value, and at last we take the final breathing value of a normal breath. All of these values come together to give us the measured RV of our individual. After the RV measurement, our subject is ready to hop in the water. We will first ask our participant to go fully underwater and get any additional air bubbles out of his hair and shorts. Next, we will proceed to give the subject a weight belt that will help him stay submerged underwater throughout the test. It is important here to remind your subject that once they are seated in the swing, that their hands and feet should remain off the wall at all times. Next, explain to your subject what they will actually be doing. Allow your subject to get comfortable in the water and explain to them that they need to breathe all of their air out, either on their way under the water or once they're fully submerged. Once they have breathed all of the air they can possibly breathe out and feel like they have no more to give, to try to stay submerged under the water for at least additional 2 to 3 seconds. This allows extra time for the cell to become stable and for the people in the lab recording the data to get a more accurate measurement. Make sure, though, that you do not start to record the data until you do not see any more bubbles in the water. In this lab, we are using a Trendicator, which is a digital display device to get the underwater weigh-in of the individual. However, a chart recorder can provide a more accurate measurement and a permanent recording of the underwater weight. It can also provide us a permanent recording of the tear weight. Of all the underwater weigh-in trials, the values need to be consistent. The goal here is to find a mode. However, if you do not have repeated values, if your values are close and somewhat consistent, you can take the average of the two closest values. Again, to get the most accurate values, we have encouraged our subject to exhale all of the air and stay under as long as possible. However, this procedure is done at one's own pace. So, ask your subject to stay under the water as long as they feel comfortable and that they can come up above water when they need to. After we have collected all of our trials, we will make sure that we get the tear weight by asking our subject to stay in the water and rest the belt over the seat so we can measure the weight of the belt and the seat together. This is called the tear weight. In summary, the purpose of this lab was to become familiar with the techniques used to determine body composition from underwater weighing and the underlying differences between body volume and body density. In addition, you should be familiar with the physiological differences of fat and fat-free mass. Specifically, this lab gives you an estimated analysis of fat and fat-free mass using body composition measurements that include a gold standard method of determining body composition and body density. With this information, clinicians are able to gain a more in-depth understanding of an individual's body composition, rather than relying on body weight alone or body weight relevant to height, to determine a proper course of action moving forward to improve and maintain their current health status.